Hello and welcome to another video. In this video we're going to be working on power 4, and it's a pretty straightforward problem. Given an integer n, return true if it is a power of 4. And if it's a power of 4, there exists an integer x such that n equals 4 to the x. So for 16 there is an integer x, right, because 4 squared equals 16. For 5 there is nothing, and then for 1 there's also 4 to the 0 equals 1. So there's a bunch of ways, obviously, to do this with like a binary search, where essentially you can just look for a number, 1 to whatever n, and then just see like, is 4 to that number your number, or is it too big or too small, and something like that. So there's a bunch of these logarithmic solutions. You could do that. You could divide the number by 4 over and over and over. See if you get like a see if you get a remainder of 1. Essentially, it should be like 4 times 4 times 4 times 4 times 1 or something, right? In order for it to be into power 4, some kind of like 4 to the x, basically, times 1. So you just keep dividing by 4, and you have to make sure you get 1, and if you do, then you have an answer. Otherwise, if you get something else, then you don't. And these are all like logarithmic solutions. But what we're going to do is we're going to do a bit manipulation solution just because it's an easy problem. Definitely not super intuitive, but once you see it, I think you will get it, and you might be able to like use it in the future. So let's write down some powers of 4, just to get some intuition. So 4 to the 0 is 1. So that's just going to be 1. 4 to the 1 is 4, so it's going to be 0 in the 1s, 0 in the 2s, and 1 in the 4s. 4 to the 2 is 16, so 0 in the 1s, 0 in the 2s, 0 in the 4s, 0 in the 8s, and a 1. And finally, we'll do one more, 4 cubed, which should be 64, I believe. So 0 in the 1s, 0 in the 2s, 0 in the 4s, 0 in the 8s, 0 in the 16, 0 in the 32, and then this. So essentially you see a pattern, right? For every power of 4, it has a 1 and then an even number of zeros, right? And you can keep going. 4 to the 4 would just be, like this is 2 zeros, 4 zeros, 6 zeros, 8 zeros. And it makes sense, right? Because every power of 4 is just basically a 1 and a bunch of zeros. Now let's also write down powers of 2, which we're going to use. So let's write down a few of these. So let's just do 2 to the 1, 2 to the 2, 2 to the 3. These are going to be a lot easier, right? Maybe we'll do like a few. Okay, there we go. So powers of 2 are obviously very easy to write in binary, right? It's literally just 1, and then 1, 0, and then 1, 0, 0, and then 1, 0, 0, 0, 1, 0, 0, 0, 0. So essentially, powers of 2 can be powers of 4, but not all powers of 2 are powers of 4, right? Like a 2 is not a power of 4, and as you can see, so it's like every other power of 2 is a power of 4. So this is a power of 4, this is a power of 4, this is a power of 4, right? So what we're actually going to do is we're going to first figure out, is it a power of 2? And how do we do that with bit manipulation? So that one is pretty easy. First of all, any number that's greater than 0, like let's just say we have some random number like this, right? What we're going to simply do is any power of 2, to know that it's a power of 2, if you AND it with that number minus 1, right? And that number minus 1, like what would this number minus 1 be essentially? So this number minus 1 would be this turns into 0, and then these all turn into 1s, right? It's kind of like the same thing as like if you have, 1,000 in decimal minus 1, right? You would just get like 99999, whatever. Like 1 and a bunch of zeros minus 1, same kind of thing in binary. So if you subtract 1, you would get 1, 1, 1, 1, 1, 1. And now if you AND these, then this will be 0, right? Because everything is 1s and 0s. There is nothing else. But if you have any other non-zero number, like let's just say we have some random number, let's just try a few numbers, and let's try the kind of like the same operation. So let's just add a 1 somewhere, maybe. Like let's add a 1 here. So what would happen here is when you do this, minus 1, you would get 0, 0, 0, 0. Then these would all be 1s, right? So actually, this is a power of 2, so this would actually work. So let's get a non-power of 2 number, right? So we have to get a number with like multiple 1s essentially. So let's do something like this. There we go. Okay. So now what would happen here is if you subtract 1, you would get 1, 0, 0, and then this would become a 0, and now these would all be 1s. And then when you AND this would be non-zero, right? So that's like one number we tried. Let's try a few more. Let's say we have something like this. But the basic idea is anytime you have more than 1 in the number, when you subtract 1, you're going to keep a 1, like you're going to keep a 1, right? No matter what. You can't, like if the number is not a power of 2, if you have more than one 1, by definition, you're either going to get rid of one of the ones or you're going to borrow from one of the ones, but like your leftmost one will stay a 1. So like this -1 would be something like this, 0, 1, 1, and then you're still keeping this one, so this is non-zero. So essentially, the way to test if it's a power of 2 is n and n minus 1 needs to be 0. And we can do that in a O of 1 operation, right? So as long as n is greater than 0, this will work. Because for 0, it would be weird to get negative numbers, but either way, 0 isn't a power of 4, right? Because 4 to the 0 is 1, and any negative number can't be a power of 4 either, because 4 to something can't be negative, right? So we'll just check for non-zero to get rid of all those like weird edge cases. So now that we know how to get the power of 2, now we just have to figure out how to get a power of 4, and right? And half of the powers of 2 are powers of 4, but which ones aren't, essentially, right? So the ones that aren't are this, and then if we keep going, right, it's basically any one of these. So essentially, if you write down a bunch of bits, right, if you look, the ones that aren't, the even bits are 1s, right? So the power of 2s that aren't a power of 4, the even bits are 1s, right? Like 0, 1, 2, 3, or I guess it would be the odd bit or whatever, right? Like basically it's these ones are not. So if it's, I guess it depends on which way you count. But essentially, for every 4 numbers, one of these 2 bits is a 1 and not these 2 bits, right? Because if you look, which ones are powers of 4s? It's these. So it's this bit and this bit are 1, and you can keep drawing this out more. And for powers of 2, this bit, or in powers of 2, any one of these can be 1, but essentially it's starting from here, the second or 4th bit, or 6th bit, or 8th bit, or so on, is a 1 for a power of 2 that's not a power of 4, right? These two things. So essentially, what we can do is we can take our number, like let's say we have, for an example, let's say, so 4 to the 3 is 1 and 8 zeros. Let's say we have 1 and like, so clearly, as you can see, like it's 1 and an even number of zeros. So let's say we have 1 and like 16 zeros or something nuts, right? So 1, and then we have 16 zeros. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this would be some power of 4, right? And basically, all we have to do is just figure out like where is this 1 at, right? It's somewhere because it's a power of 2, but we just have to make sure that it's in a slot for a power of 4, and we have to do that in O of 1 time. So the way we're going to do that is we're actually going to AND with this right here, with just like a bunch of these. So if it's a 32-bit number, we can just do 8 of these. So by the way, what is this? Well, actually, we'll get into that, but essentially we can AND with 8 of these. So we're just going to AND with this thing here. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. And so when we AND these together, this will be 0, but notice that this basically checks like, is the 1 in the valid location? And for a power of 4, it has to have an even number of zeros behind it, right? So for a power of 4, it has to either be in this location, in this location, this location, this location, so on, right? All these locations have an even number of zeros. Like this has 2 zeros behind it, this has 4 zeros behind it, 6 zeros, and so on. So essentially, you just AND it with a number that, you know, if you did have a 1 where it can't be in these odd locations, right? So like this location here, 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 and so on. It has to be in 0 location. That way, if you have a 1 in a 0 location, 1 in a 0 would be 0, and then all of these rest would be 0, essentially. So now we have to figure out, like, for the 32-bit number, what is this equivalent to? And we're just gonna make like 8 of these to essentially AND with however big our number can be. So what is this equivalent? So this is actually 10. And so the way we could do this, the way you could do it, like, and people do this, so you can actually write a number in hex. So a number in hex is 0x, and then every digit is 4 bits. So we just have to figure out, like, what are 4 bits to 10. And the way hex works is it goes 0 to 9 for the first 9, and then it goes A, B, C, D, E, F. So because this is 10, this will be A. So essentially, we just have 8 of these A's. So we have A, A. And that's a 32-bit number. That's just a bunch of these 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So basically, to recap, we have to do n minus 1, figure out if it's a power of 2. And then we know that our number will have the form of a bunch of zeros, and then it will have 1, 1, 1 in the number at some location. And for a power of 4, half of those locations are valid, right? Half of them are valid. So as you can see, like every location where there's a 1 and an even number of zeros is valid, and every location if there's a 1 and an odd number of zeros is invalid. So we just AND it with this thing, and basically this puts a 1 in every single invalid location. And if we have a 1 in an invalid location, and it would AND with one of these ones, we would get a 1. And if the 1 is in a valid location, then we would AND it with a 0, and this whole thing would evaluate to 0. So essentially, if this is true, and with 0x a is also 0, that means it's a power of 4 that is in a valid location. It's obviously also a power of 2, because every power of 4 is a power of 2, but not every power of 2 is a power of 4. So this tells us if it is a valid location, and this tells us if it is in the form of a bunch of zeros and just 1, 1. And that's pretty much all we need to solve this problem. So yeah, I do recommend if you find this hard to understand, like draw this out for a few numbers and figure out exactly why this is. But basically, this is how you do it, and it is valid to write down numbers like this in Python. I think in other languages there might be like some other ways of writing it, but essentially you can write a number in hex, and that's the easiest way. I don't know if you can write a number in binary. Maybe you can. I think you might be able to also write in octal. I don't know if you can do it in Python, but octal looks like 0 and then a bunch of other stuff. But hex is the easiest way here. So we're going to write it in hex. So let's code it up now. So we're going to say if, or I guess we can just return if all these things are true. N is greater than 0 because it has to be 1 or more. And n minus 1 is also true, which means it's a power of 2. And we have to check for a valid power of 4 now that we know it's a power of 2. So n and 0x and then 8 a's, because each a is 4 bits and it's a 32-bit number. So 2, 3, 4. And there we go. And hopefully this is correct. Let's take a look. And there we go. Oh, looks like we don't. Oh, right. So we screwed this up a little bit. So these need to be 0, right? So these need to be 0. There we go. There we go. Okay. And yeah, so there we go. So we have an O1 solution. And I do think like it's kind of cool to learn how to do the power of 2 in O1 time. And I think it makes perfect sense if you think about it. Like if you know that a power of 2 is just 1 and a bunch of zeros, if you subtract 1, it's 0 and a bunch of 1s. You can AND it with that. You can figure it out fast. This power of 4 thing is a little bit less useful, but the power of 2 thing is cool, so I just wanted to show that. And yeah, if you do see that, now you can do it really fast. So yeah, that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.